All right, here we go. Here's a collision problem. You can pause for a second and read the question head before continuing on. And hopefully after you've read it, you'll realize that this is a collision problem in which there's a cue ball that hits an 8 ball that was originally stationary. And then after the collision, the cue ball goes to this direction and the 8 ball goes this direction. So I can, first of all, label my axes. So this is the original situation before the collision. I'm going to choose this to be my positive x. I'm going to choose this to be my positive y. And then after the collision, here's the x and y axes. And I am told that this velocity at the beginning was 4 meters per second in this particular direction, and I'm given some dimensions to determine what the direction is. So this triangle for the direction looks like this: 0.6 meters, 0.8 meters. So if I calculate this c, which is the length of the hypotenuse, that's going to be the square root of 0.6 squared plus 0.8 squared, which is 0.6 squared is 0.36, and 0.8 squared is 0.64. 8 is 64. So that adds up to 1. So c is going to be equal to 1. So then I know from that that if I call this the angle theta, then I know that cosine theta is going to be equal to 0.8 over 1, and sine theta is going to be equal to 0.6 over 1. So that's the direction of the original velocity, and its components I can figure out by knowing the cosine and the sine of the angle. Okay, and we'll see why we need this. After the collision, the cue ball just goes along the positive x, the 8 ball goes around along the minus or the negative y. This is a collision problem. So I'm thinking about what happens during the collision. Are there external forces that are acting? What is the impulse? And because that is going to tell me the change in momentum. So we'll take a look at these things. First of all, are there any external forces? Because the impulse is equal to the external force multiplied by the time it's acting. And of course, if I consider the 2 balls to be my system, and I'm told that the table is frictionless, then I can see that if I look at this is the pool table right here, the surface of the pool table, and there's the weight of the ball, and there's the normal force, and because there is no acceleration in the vertical direction, which is going to be perpendicular to the surface of the table now, then there is no external force in that direction, and because there is no friction alongside of the table, then there's no external force. So all of this is just to say that there's no external force acting on the 2 ball system. If I just consider one of the balls as being my system, then of course the balls are going to hit each other, so they're going to exchange forces. They're going to act on each other with forces. So if I consider each ball to be my system, there will be an external force. But if I'm considering the 2 ball system together, there is no external force acting on them. And because there is no external force, there will be no impulse of external force. So we know then that the change of momentum of the system, which consists of the 2 balls, which is equal to the sum of the momentum and the final minus the sum of the momentum initial, then that's going to be equal to 0 because there is no impulse of external forces. And of course, this is a vector equation, so I can think about it in terms of the 2 components independent of each other. I can think of the x component dependent of the y, and I can think of the y component independent of the x component. So now that I figured out that the change momentum is equal to 0, what is the momentum before and what is the momentum after, and if I subtract them from each other, that should be 0. So the momentum before the collision means that I have to look at the system before the collision, what the different velocities are, and we agreed that we're going to look at it in the terms of the two dimensions, the x and the y, independent of each other. So if I'm looking at the momentum here, the momentum is equal to the mass times the velocity. And I could look at it as components. The x momentum is the mass times the velocity in x. The y component is the mass times the velocity in y. So if I wanted to sum up the momentum before the collision, this is going to be the sum of the momentum of the cue ball and the momentum of the 8 ball. The 8 ball has a velocity of 0 because it's at rest before the collision. So the momentum before the collision is only going to be the momentum of the cue ball. And I want to look at that in terms of the x momentum and the y momentum. The x component of the momentum is going to be the mass of the cue ball multiplied by the velocity, the x component of the velocity. So that's going to be equal to the mass of the cue ball multiplied by the velocity v naught cosine theta, because that gives me the x component, and that's going to be positive because it's pointing in the positive direction of what I've chosen to be the positive direction of x hat. So then that's going to be equal to v naught is 4 meters per second as I'm given, cosine theta is 0.8, 0.8 times 4 is 3.2. And I could put in the mass, which I know I was told in the problem what the mass is, but I could just leave it out. And because I know that the mass is also going to be part of the momentum after, and the two balls have the same mass, so I know that the mass is going to fall out of the equation because it's going to be mass times velocity equals mass times velocity. So the mass is going to come out. So I'm just going to leave the mass as m, and we said 4 times 0.8 is 3.2 meters per second. So that's the x momentum to start with. The y momentum to start with, again, the 8 ball is at rest, so it's not going to contribute to the momentum. So it's only going to be the one for the cue ball, and that's going to be the mass multiplied by the y component of the velocity. The y component of the velocity is going to be sine theta, and it's going to be pointing down, so I'm going to give it a minus sign. So that's going to be equal minus m. Sine theta is 0.6 times 4, that's 2.4 meters per second. Now, after the collision, I'm going to label my velocities as v1 for the cue ball after the collision and v2 for the 8 ball after the collision. So then, after the collision, the x component to the velocity of the momentum is only going to be the contribution from the cue ball because it's only along x. The 8 ball goes along y, so it does not contribute to the x momentum. So it's only going to be the mass times v1, and that's going to be equal to the v1 is something that I don't know, so I'm just going to leave it at that. The y component of the momentum after collision is only going to be the contribution from the 8 ball because the cue ball is all along x. So that's going to be v2 multiplied by the mass of the 8 ball, but the mass is the same for all of the balls. So I'm just going to leave it at that. And I'm just going to give it a minus sign because it's pointing in the minus y direction. Okay. Now, if I go back to what we said here about the the impulse of external force is equal to 0, so the change in momentum is equal to 0. So that means that the x momentum before the collision is going to be equal to the x momentum after the collision, and the y momentum before the collision is going to be equal to the y momentum after the collision. And very quickly you notice that the mass is going to fall out, so V1 is going to be equal to 3.2 and V2 is going to be equal to 2.4. So if I then say that the change in momentum is equal to 0 because the impulse due to external forces is equal to 0 because there is no net external force, then from that I will figure out that the x component of the change in momentum is equal to 0, which tells me that V1 is equal to 3.2 meters per second, and the change in momentum in the y direction is equal to 0, which tells me that V2, I've already assumed that it's going in the minus y direction, so it's just going to be equal, its magnitude is going to be equal to 2.4 meters per second. And that's what's required in part A. Now for part B, the question is, what type of collision would you classify the contact between the two balls to be and why? Well, the types of collision that we have are basically in all kinds of collision, the momentum is conserved. Okay, if the external impulse is equal to 0, and that's what we realized before when we solved part A. But also, in the case of elastic collisions, the kinetic energy is also conserved. In the case of inelastic collisions, kinetic energy is not conserved before and after the collision. And in the case of completely inelastic collisions, of course, the kinetic energy is not going to be conserved because that's part of an elastic collision, inelastic collisions. But also, in the case of completely inelastic, the objects are going to travel as one. Obviously, the objects don't travel as one after the collision, so it's not going to be completely inelastic. So it's either going to be regular elastic or regular inelastic, depending on whether the kinetic energy was conserved or not. So that's what I need to figure out. Was the kinetic energy conserved? Okay, so this is what I'm going to calculate next to figure out whether the kinetic energy was conserved or not. So for part B, I'm going to look at the kinetic energy before and the kinetic energy after the collision. What do I know about the kinetic energy? Let me find my note about kinetic energy. Here it is. So for part B, the kinetic energy is equal to half mv squared. So if I'm trying to sum up the kinetic energy before the collision, I have to sum it up for all constituents of the system, and then I'll do it for all constituents of the system after the collision. So before the collision, I had the total kinetic energy was equal to half, for the Q ball, it was half m v naught squared, and for the 8 ball, it was 0. Because the 8 ball was at rest, so its velocity was 0, so its kinetic energy is 0. And then after the collision, the total kinetic energy is equal to half m. For the Q ball, it's going to be its velocity squared, and for the 8 ball, it's going to be its velocity squared. And of course, the direction doesn't matter in the kinetic energy because it's a scalar quantity. So it's half m v1 squared plus half m v2 squared. This is for the Q ball, and this is for the 8 ball. Okay, notice, like I said, that this is a scalar quantity, so I did not have to break it down into the x components or the y components to figure out if the kinetic energy was conserved. The kinetic energy is an energy that's associated with the velocity squared, so the speed squared. It's not a directional thing. So the kinetic energy just has to be conserved as a scalar quantity. So that's why I did not stress the direction of the velocities. It does not matter. Okay, so before, that means that it's half m. V naught was 4 meters per second. And after, I can take the mass common because it's the same mass for both balls, and v1 squared, v1 I've calculated to be 3.2 meters per second, all squared, and v2 is also 2.4 meters per second. Is something that I found in part A. And then the question, really, to figure out whether the collision was elastic or inelastic is whether the kinetic energy is conserved, meaning that whether it's the same before or after the collision, or whether it was not conserved, meaning it was different after the collision than before the collision, whether we lost some kinetic energy. So the question is whether 4 squared is equal to 3.2 squared plus 2.4 squared, and of course is going to be equal to knowing what we know from before, but you can just work it out. So you can ask yourself whether the kinetic energy after minus the kinetic energy before, whether it's going to come out to 0 or not. So that's half m, and that's 4 squared minus 3.2 squared minus 2.4 squared. And if you work it out, you'll find that it's equal to 0. But also which means that the collision is elastic. Now for part C, the question is, what are the magnitudes and directions of the average forces that the balls exert on each other? And now that's an interesting question because, of course, if I consider the two balls as the system, then the forces they act on each other are considered internal forces. But now that if I consider one of the balls, either of the balls, to be the system, then the force that the other ball exerts on it is now considered an external force. And we know from Newton's third law that these two forces are going to be equal in magnitude and opposite in direction. So now what I could do to find that out, because I know that the average force multiplied by the time of action is going to be equal to the impulse, but at the same time I know that the impulse is going to be equal to the change in momentum. Then if I look at the change of momentum just of one of the balls and look at the impulse generated by that change in momentum, that could give me the average force knowing the contact time. And then, of course, once you get one of them, then the other one by Newton's third, you can get it. But in this example, I'm going to solve it both ways so that you would see how it's done. Or I'm going to solve it for considering the 8 ball as the system of interest and then considering the cue ball as the system of interest. I'm going to look at the impulse of external forces as being the change in momentum, and of course it's a vector equation, so that means I could do it in both x and y independently. So I'm going to look at the external impulse due to external forces in the x direction, and I know that that's going to be equal to the change in momentum in the x direction for the 8 ball. So that the change in momentum, of course, is the final momentum minus the initial momentum. And remember, the 8 ball initially was at rest, and then finally was moving in minus y. So initially it had no x component to the momentum, and finally it has no x component to the momentum. So in fact, this is equal to 0. Now as for the y piece, this again is the change in momentum in the y, and that's going to be equal to the final in the y minus the initial in the y. And remember, we're calculating this for the 8-ball, and the 8-ball again was 0 to start with, no velocity, and then the velocity, the final, is v2, which we calculated to be 2.4 meters per second in the minus y direction. So the final momentum is going to be equal to the mass multiplied by v2 minus the initial momentum is 0 because it was at rest, and the mass is given as 0.165 kilograms, and the velocity is minus 2.4 meters per second in the y direction. And I'm just going to keep this minus sign. I'm going to keep it hanging out with me so that I remember what the direction is. But it's not necessary because I'm just talking about magnitudes. So I can just leave the minus sign out of it as long as I remember which direction it is. But since I decided that the positive y is going to be up, then I'm just going to leave the minus sign hanging out with me. Now, I also know that this impulse is equal to the average force multiplied by the time of action. So I know that Jy is equal to the impulse in the y direction is equal to the average force in the y direction multiplied by the time of action. And then that implies then that the average force is equal to the impulse divided by the time. And the average force, in this case, the force that I'm talking about is force 2, because it's the force acting on the 8-ball. And that force is all in the y. So in fact, this is just average force 2. So I can just write that as average force 2 is equal to this momentum in the this impulse in the y direction divided by the time of action, which is 2 times 10 to the minus 3 seconds. And if you work that out, you'll find that it's 198 newtons, or 200 newtons roughly. And like we said, this is in the minus y direction. So I could just say then that F1 is equal to also 198 newtons, but in the plus y direction. But I could redo this calculation for the cue ball just to see one more time how it's done. So considering the cue ball as the system, I can redo the calculation. I say the impulse in the x direction is equal to the change of momentum in the x direction, and now that's for the cue ball. And for the cue ball, the final momentum was all in the x direction, and the initial momentum had some component in the x direction. So the final momentum was all in the x direction. The initial momentum of the cue ball had some component in the x direction, v naught x multiplied by the mass, and that is the mass multiplied by 3.2 meters per second. So first of all, the final momentum is equal to, the final is the mass multiplied by the velocity, the final velocity of the cue ball, so that's 3.2 meters per second, minus the initial momentum, and the initial momentum was the mass multiplied by v naught x, which is also 3.2 meters per second, and that is going to come out to 0, which is a good confirmation to the fact that it would be exactly opposite to F2. So it would have the same x component, which is 0. And then the y piece now is the change in momentum in y. And the change in momentum in y is the final momentum in y minus the initial momentum in y. And that's equal to the final momentum in y for the cue ball is 0 because it's moving just along the x-axis. So it has no final momentum in y. So that's 0 minus. The initial momentum in y is equal to the y component of this velocity multiplied by the mass of the ball. So the y component of this velocity was 2.4 meters per second pointing down. So this is the final momentum in y. So that's the mass multiplied by minus 2.4 meters per second. So that's equal to the mass multiplied by the two minuses go away, 2.4 meters per second. And then just like we said before, but I know that Jy is equal to the average force in the y direction multiplied by the time of action, which implies then that the average force in the y direction is equal to the impulse in y divided by the time, which says that in this case, this is the average force 1, because that's the force acting on the cue ball, that's the net force on the cue ball, is equal to this impulse divided by the time of action, and that would be equal to 198 newtons in the y direction. Notice that it's exactly the same magnitude, but in the opposite direction as F2 as expected.